I'm very glad to present our speaker today, Tanmay Vachaspati. He's from here, Arizona State University. Anyway, I'm very glad that he agreed to give a talk at the last moment because we had some mix up with the speakers. Tanmay received his PhD at Tufts University in 1985, working with Alexander Vilenkin, who's famous for many things, just like Tanmay is. Tanmay had several postdoc positions at the University of Delaware and Cambridge. Then he got some professor positions at several places. In the end, he ended up to make his career primarily at Case Western University, where he spent, I guess, something over 10 years. He moved to Arizona State University in 2010 as a director of cosmology initiative, and he was a full professor. He spent some time on some visiting research professor positions, at least a year in Maryland, not so recently in 2016, 2017. And obviously he is an expert on cosmology, magnetic fields in early universe, and he will be giving a talk today about the magnetized universe. So with that, please, Tanmay, you may start.
Okay, well, thank you, Igor. Thank you for organizing this wonderful colloquium series. And thank you all for coming. I am obviously going to be talking about the magnetized universe. And this is a subject which is quite old. I mean, I'm starting from Harrison or even earlier, and so that it's quite broad and it's quite vast. But I will try and sort of take you through some essential things, and then also sort of discuss the more recent recent advances in this subject. So let's see. So basically, this talk will have three components. One is the observations, so what progress has been made on the observation side, and then of course that leads into the early universe, like how could we produce these magnetic fields? But that sort of relies on how magnetic fields evolve, and so there's MHD coming in, and maybe chiral-MHD, and then actually I'll cycle back to observations, and maybe come back to the early universe. So it's a kind of a going round and round this triangle over here, but it's an interesting story, and I hope you'll enjoy it. So let's start with observations. These observations have been done by many groups and over many decades. And I obviously can't discuss all of them. But if you're interested, then there are these reviews, several reviews now that you can consult. The first observation, of course, is galactic fields. Our galaxy has about a micro-Gauss magnetic field. And there's been a debate whether this magnetic field came from the early universe or whether it was generated by a dynamo, which needs a seed, but then the seed, maybe some astrophysics can produce that seed. So that's the first observation. But then you also have micro-Gauss fields in galaxies at very large redshifts. And so it seems that maybe there's not enough time for a dynamo. So that would suggest that maybe it has to be a primordial field. Then there's Faraday rotation of quasars. So you know that the linear polarized light, its polarization direction will rotate as it goes through a magnetized plasma. And so the Faraday rotation gives you upper bounds of about a nano-Gauss, that's 10⁻⁹ Gauss on coherent magnetic fields, coherent meaning, say, between here and the quasar. Then there is a Big Bang nucleosynthesis upper bound, and that is a weaker bound. It's at the micro-Gauss level. Remember, the quasars were at nano-Gauss, but this was at micro-Gauss. But it's really a constraint on the energy density of the fields, and it doesn't really care about the coherence of that magnetic field. Then there's the CMB, and then people have worked out the temperature anisotropies and B modes that would be produced if you had magnetic fields. And again, the upper bounds are at the sort of nano-Gauss level on coherent fields. More recently, there's been some discussion of inhomogeneous recombination that would affect the CMB, and I will come to that a bit later. Then you have the blazar observations, and these actually give you lower bounds. So these are lower bounds at the 10 to the minus 16 Gauss on megaparsec scales. So these are some of the observations, and obviously there are others that I have not put here. So just to sort of make a summary plot of these bounds, oops, sorry. So here there is a magnetic field on a certain scale C. So that's the coherence of the field. And here I go from 10 to the minus 6 Gauss, where there's a galaxy, and then goes down to about 10 to the minus 16 Gauss or so. And then there are various values of C, kiloparsec, megaparsec, gigaparsec. Of course, nothing is to scale. And the BBN bound constrains the energy density up here. Quasars are somewhere around here. Quasars, CMB, ultra high energy cosmic rays, they constrain U to be less. And the blazars over here seem to be saying that the magnetic field is larger than something. And just to give you another data point, there's this box over here, the golden box. And this part is interesting because if you have magnetic fields over here in the early universe, then they can directly produce the magnetic fields in galaxies. So you don't need much dynamo to amplify those fields to get the galactic field. There are several other constraints, notably a very recent paper by Sonati et al., where they're using the structure of dwarf galaxies to put constraints on the magnetic fields. And you can look up that paper.
Tanmay?
Sorry, yeah?
Somebody has a question in the audience. Anastasia, would you like to ask yourself?
Yes, I have a question. So we know that magnetic fields exist because we see magnetic fields in galaxies. And I have a question. What is the lower bound on the magnetic field at the time, for example, during CMB or at redshift 100? During, between like 1000 and 100, where it just scales as a squared.
Sorry, so do I understand that there's another constraint?
No, I'm just asking because, for example, if the magnetic field is equal to 0 during CMB, then we would not have any magnetic fields today, right? So yes, we should have some very, very small magnetic fields during CMB to have magnetic fields today. And I'm asking, what is the minimal value for this magnetic field?
So the usual story is that the galaxy has rotated about 50 times. So, and if you assume a sort of a maximal dynamo, then the magnetic field would have gone to e to the 50. So then the seed field you would need would be e to the minus 50 times a microgauss. But of course, this doesn't work when you have magnetic fields in early galaxies. There's also a paper by Kulsrud and other people who say that maybe there's some astrophysical shocks that happen when when structure forms, and then you don't even need a seed field, because those shocks would produce the seed fields by the Biermann battery kind of mechanism. So so there are lots of different scenarios, but one number would be e to the minus 50 times the microgauss.
Okay, thank you.
Thank you for the question. Okay, so let's go on. So let me discuss the blazar cascades, which are sort of, because they give a lower bound, and in some ways they're the most interesting. So let's say you have a blazar up here, and it's shooting TeV gamma rays, and we are down here, of course, so it's shooting it. So you're looking down the barrel of the gun. And so then we know how TeV gamma rays propagate. Occasionally, what's going to happen is that this TeV gamma ray will hit an ambient photon, say coming from starlight, from somewhere, so some stray photon. It's called the EBL, the extragalactic background light. And because of that interaction, it will produce E plus E minus pairs. And the E plus E minus pairs will then go further and upscatter the CMB photons to GeV energies. So basically you have a TeV source, but then you're getting photons which have downgrade, well, you're getting photons at the GeV scale. So if you look at the morphology of this beam that is coming down, you would see a TeV interior, and then a GeV halo around the TeV interior. So basically what's happening is, because of the EBL photons, if you look at the flux of photons, then let's say you start with this black curve over here. What's happening is that some of the TeV photons are being depleted. So this spectrum comes down. And then these photons are then producing these GeV cascades. So then the GeV part goes up. So what you have is a decrease in the TeV flux, but an increase in the GeV flux. And okay, so we'll discuss the effect of magnetic fields later, but yeah, so this is what you should see: a decrease in the TeV and an increase in the GeV. So Neronov and Wolf and Essi, Ando, and Kosenko, and now several other groups have looked at these blazars. And so let me just go over one data set. So here's the data, and this is at roughly TeV energies, okay? So then they have a model of the EBL, and they can estimate what the primary unabsorbed spectrum would be, and that looks like this. And then they can estimate how many GeV photons should be there. And they have this curve, and if they add up the GeV and the TeV, then they get this processed spectrum, which goes through the data points at TeV energies. And then they say, do we see this excess because of this cascade? And so they look at Fermi, the Fermi data, and Fermi puts a bound which goes like this, okay? So basically these photons, which you should have seen as a GeV excess, are actually missing. So then you have to come up with a mechanism for getting rid of these GeV photons, and that's where magnetic fields come in. And you need a strong enough magnetic field to cause this depletion, and so that gives you a lower bound on the magnetic field. So here's the effect of a magnetic field. If I put a magnetic field over here, then the E plus E minus pairs that are being produced over here, they get bent and they get scattered, so they get wider angles, and the flux of GeV gets diluted. So this was a morphology earlier with zero magnetic field, but with a magnetic field, you might expect that the GeV halo is much larger, and you would see a smaller flux, if anything at all. And so Neronov and Wolf put a constraint of about B should be larger than 10 to the minus 16 Gauss. And other groups have also looked at it, and I think including Fermi, and they have placed similar, maybe a little weaker bounds, but there is a lower bound on the magnetic field due to these blazar observations. So as you notice, what you're saying is that I'm not seeing these photons, and so there must be something to explain that. And so the Neronov and Wolf and others are saying that it's due to a magnetic field. But there's another group, Broderick, Chang, and Frommer, and then other collaborators who say that this dilution could happen due to plasma instabilities.
Sorry.
Sorry?
There's a question, if you don't mind.
Sorry?
There is a question from the audience, if you don't mind.
Sure.
Okay, go ahead, Camilo.
Hello. Is it possible to put error bars on this lower bound?
So I think there's a lot of, it's not a firm number like they're saying that that we've observed such and such, and so these are the error bounds. They are just putting constraints, and actually when different groups do the analysis, then they get constraints that change by maybe an order of magnitude. So I don't think we're at that point, and maybe I'll make a brief mention about this later on. Right?
Thank you.
Right. So then let me go back here. So then there's this debate whether it's plasma instabilities or it's a magnetic field. And so these authors, Chen, Buckley, and Ferrer, and earlier Ando and Kusenko had also tried to do a similar analysis. They said, well, the halo might be too dilute for just one source, but what if we stack lots of sources, then we might be able to see the halo. And so this is from the paper by Chen, Buckley, and Ferrer. They compare two different kinds of sources, one for which you expect the halo and one for which you do not expect the halo. And then they compare the two. And the differences are in this plot over here, and you can see that there is some excess halo for the sources where you do expect a halo to be present, even if it's dilute. And here's another plot. The blues are lower than the red, as you can see. And so there's a shortfall over here, but there's an excess in this region. And so basically they are saying that they've detected the halo at about 3.5 sigma. So if this is the right picture, then I think the case for magnetic fields is greatly strengthened. Okay, so sort of continuing with the observation theme, now I would like to discuss a very recent paper by Jadamzik and Pogosyan, who were considering the CMB with a magnetic field. Now the CMB only looks at very large length scales, so they can only say something about the magnetic field on very large length scales. But these authors, they decided to look at recombination with B. And so basically they realized that the magnetic fields at recombination, if there are small scale, strong magnetic fields, they would induce inhomogeneities in the baryon density. And since the recombination rate is proportional to the expectation of NE squared, which is the square of the electron number density, and expectation of NE squared is larger than the expectation of NE whole squared. So using that, they said that basically magnetic fields would induce an earlier recombination. And because of that, the sound speed, the sound horizon, which is I denote by R star, would be lower at recombination, would be smaller at recombination. So if this was the effect, then this would shift because the peaks of the CMB are located at the distance to the last scattering surface divided by this sound horizon. So if this was the only effect, then the peaks would shift. However, we know the peaks very well. So the only option would be to have a last scattering surface which is closer in, and which means that H naught would be larger. So they are saying that there's a tension in H naught, and that tension can be resolved with a magnetic field during recombination. And so here's a plot. So they're looking at the clumping of baryons, and they have some probability distribution for the clumping, and they have two different models that they analyze, and they get a non-zero clumping parameter. And because of this, they can deduce probability distribution for H naught, and this is what Planck gives you for lambda CDM, and this is what they get in their models. And the H naught from surveys which are closer in give you something like 72, 74. And of course, this is the discrepancy, but they're saying that with this baryon clumping, this discrepancy can be reduced. And similarly here, this is the galaxy clustering parameter. This is H naught, and Planck is giving you here. Other data is giving you here, but with a magnetic field, you would get something that is closer in. So, so the magnetic fields that they need is about 0.05 nanogauss at kiloparsec scales. Now, kiloparsec is about the smallest scale magnetic field that would survive from the early universe. It's because there are always dissipative effects. And so this is at about kiloparsec scales. So if you have such a magnetic field, then it could solve the tension in S8 and between Planck and DES. Okay, so this you might consider, I think this is quite exciting because so this is relatively fresh, but if this becomes the, if the experts agree, then this would be evidence for magnetic fields at the earliest times that we know, right? So that would be at recombination. So it's very exciting. And so let me, so then basically here's that same plot that I showed earlier. And basically they are saying that baryon clustering would need magnetic fields up here. And as you can see that this would fall in this golden box, and then this could give you the galactic magnetic fields directly with minimal amplification. Okay, so that's observations. And now I would like to sort of switch gears a little bit and ask about the origin of such magnetic fields. And this has been a theorist's paradise in many ways. This is the inflationary mechanisms, Electroweak phase transition, there's the QCD epoch. And then earlier efforts dating back many decades was that if there's turbulence at recombination, and then there are always astrophysical possibilities. All of these, except inflation, give you magnetic fields which are causal. So they are sort of, you have stronger fields on small scales and larger, and weaker fields on large scales. But inflation might give you a scale invariant or a different spectrum. So before going on, I'd like to just say that the usual discussion of magnetic fields, which are stochastic, so you normally think of a magnetic field as being a vector field pointing in some direction. But here we are thinking of a tangled magnetic field, so it's stochastic. And it's isotropic, so there's no preferred direction when you average things over. And so you have to discuss it in terms of a correlation function. So you have BIK, this is the Fourier transform of the magnetic field. So when you take the correlator, then you have this power spectrum, which is EM. And you have a second kind of spectrum, which is called the helicity spectrum. And this helicity spectrum will play an important role a little later. To understand this, helicity is basically something like B dot curl B here, okay? So it's, if you take the curl, then that is in, how much of it is in the direction of the magnetic field itself. Or you can think of it as in terms of circular polarization of the magnetic field. Or you could think of it as this particular integral, which has something to do with linkage number of the magnetic field lines. So, so there are two spectra that we have to worry about. One is the power spectrum, and the other is the helicity spectrum. Okay, so let's go to the Electroweak epoch. And here there have been a number of ideas. But what I want to show here is that the classical dynamics, as this Higgs rolls down, that in itself will produce magnetic fields. So I consider, here's the, say, lambda 5⁴ potential. And let's say I take the Higgs to start over here at phi = 0. It has to come down to its expectation value. And so the claim is that this dynamics itself is going to produce magnetic fields. And so rather than give the arguments, let me show you some results, some numerical results. But there are, of course, this is a very simple setup, 0 temperature, only bosonic sector, everything is classical, and there's no plasma that you put in, it's whatever is produced by this rolling. And you might say, well, this potential is unrealistic. It might be, but it's not so critical for us, since what we'll find is that most magnetic fields are produced when it's near the true vacuum. So when we're doing classical dynamics, then if you put phi = 0 over here at the initial time, then it just stays there. So you have to somehow trigger the rolling. And so a perturbation is required to start the phase transition. And it's a little bit of a detail, but I found it interesting that if you look at the energy versus field space, then phi = 0 is here, and it's at some sort of saddle point, because there are configurations in field space which have energy which is larger than that, and there are configurations in field space which have energy less than phi = eta. So what you can do is you can produce a bubble with the same energy as phi = 0. So you can just kind of shift this over, and now it's not at the saddle point, and it's going to roll down to phi = eta. So here is one of those bubbles which actually conserves energy, but is unstable to rolling into the true vacuum. So this I call the trigger bubble. And there's some parameter C which you can fix. And so this is just the modulus of phi. You also have to choose the direction of phi, because phi is a 4-component doublet. So it lives on a 3-sphere. The direction lives on a 3-sphere. And so you choose that randomly. So you have these bubbles which are being produced in random directions and in an energy conserving way. So, so then you nucleate these bubbles and you evolve the electroweak equations. The only novelty here is that there's a damping term which we've added. We solve these equations using lattice field theory inspired methods and also numerical, not numerically relativity, but numerical relativity inspired techniques. And finally, the electromagnetic gauge potential is defined in a well-defined way over here.
We have a question here.
Sorry, yeah.
We have a question.
Yeah.
Okay, sorry, probably I misunderstood. What do you call the bubble? Because I thought that in standard theory of cosmology and standard model, there is no bubbles during Electroweak epoch.
Right. There is, so in that sense, there is none, because this is just a file before. It just looks like this. There is no energy barrier. But we do need to sort of push this guy over so that it starts rolling. And basically, this is, if you wish, it's a fluctuation. In fact, there's another group which has done a similar study, and they just put some Gaussian fluctuations in the initial state.
There is another question.
Yes, my question was if you are considering a charged inhomogeneous field, no?
Just a homogeneous phi equal to 0 everywhere. And then sort of stochastically, we introduce these fluctuations. And then the fluctuations sort of drive the Higgs towards its vacuum expectation value.
There is not a breaking of the rotational symmetry in general, because you have all the possible.
Yeah. There's no breaking the rotational symmetry.
Okay, thank you.
So so we evolved these equations, and so I was here. So this Na, so you have to pick out the unbroken symmetry. And then this is the gauge field for electromagnetism, and it's defined in this way. There is this unit vector that you have to define, which is phi dagger sigma phi, sigma being the Pauli spin matrices, divided by the expectation value squared. Now, of course, at early times, so this would not be a unit vector unless eta is the mod of phi. And at early times, there are problems because the Web of phi, sorry, the expected mod of phi is 0, sorry. But at late times, there is no problem because phi is nearly eta. So this is the electromagnetic gauge potential. The electromagnetic field strength, however, is not the usual Maxwellian form. It has this extra piece in here, and that is necessary. I mean, for those of you who've looked at magnetic monopoles, Tufte first introduced this extra term, which was important for deducing that magnetic monopoles have a magnetic field. So, this is the same kind of formula, but applied to the electroweak model. So in our simulations, here are two bubbles that are nucleating, and then they have different phases. So they are pointing in different directions on the 3-sphere, and then they collide, and then this is the Higgs squared divided by eta squared. And then here is the magnetic field. So nothing to start with. and then you form a ring where the bubbles collide. So this sort of explicitly shows that when these bubbles will collide with different phases, then you will start producing magnetic fields. And you can have many bubbles and they start colliding and you get a kind of a mess. And then you have to work out the magnetic field and calculate its correlation functions and its spectrum and so on. So here's the, so I won't discuss all the things that go in, but the energy density of magnetic fields in units of mass of Higgs to the 4 as a function of time is shown over here for different damping parameters. And so you see that the magnetic field energy density keeps growing. And in this case, it's about 6% by the end of our run. We were kind of limited by computer time, so we didn't push it much further, but it still seems to be growing. So say roughly 6% or 10% of the vacuum energy is going into the magnetic field energy.
There is a question here.
Yeah.
Edward?
Okay. Yeah, it's the same question as was asked. In the standard model, we now know there is no first order transition. So bubbles.
Mm-hmm. I see. Yeah, so if the picture is different, then of course this will be modified. But here, I mean, we basically triggered the field to roll off to get a wave, and I actually, yeah, I don't know what happens if you have a crossover. So that would be something worth looking at. But what we realized is that the rolling off really didn't, the initial phase of rolling didn't really matter. Most of the magnetic field energy that was produced was while the Higgs was oscillating around the true vacuum. And after all the bubbles have collided and percolated, and that's when we produced most of the magnetic field energy. So I don't know what the picture in what will happen in a crossover. So okay, maybe someone else can.
In crossover, we don't have these bubbles, but we have sphalerons.
Yes.
There are other explosions, but not these ones.
Yes, and I'll come to that. I know your paper on that topic. Okay, so so this is just saying that if there is a simple picture that's happening and you are producing magnetic fields, you can look at the spectrum, and the spectrum looks something like this. This is K. This is a typo, Kp. So this is K, and this is the electromagnetic energy, the power spectrum. And you can see the spectrum, and then you have this funny bump, which, to be honest, I don't fully understand. But I do know that this is not a figment of our imagination. Another group did the same and did the same analysis, and they also get this funny peak at small k. So I don't fully understand why there is excess power on small scale, on small k, which is large length scales, but it does seem to be there. So one conjecture was that coherence scale would be the bubble percolation scale, but I don't know if that is true. Because the other idea was that, okay, you would produce these magnetic fields, but they would be on very small scales, small length scales, and then they might get dissipated. So I don't, so this seems to suggest maybe there's some power on long wavelengths also. Okay, so once you produce this magnetic field, how does it evolve? I just need to keep an eye on the time. Okay. let's say this is log of the power spectrum, and here's log of k, and you have some spectrum which looks like this. There's some inertial scale over here. There's some dissipation scale after which the magnetic field falls off, and then this is the part that we're interested in. This is the long wavelength modes. So there have been many simulations of the system, MHD simulations, and some analytical work. And the spectrum seems to evolve in this way. It kind of shifts to the left, but also keeps decreasing. And this shift is interesting, but it's kind of weak. But it's so what this is called, the shifting to the left is called an inverse cascade, but it's a weak inverse cascade. And so the power at large length scales, small k, remains small. So, so this would be a problem for the electroweak magnetic fields, because you are interested in getting power on large scales, on large length scales, and it's not clear how you will get that from the electroweak origin. However, if the magnetic field is helical, then here's the initial spectrum, and it just kind of shifts to the left with this part, of course, is decreasing, but this peak is kind of at the same height. And so what's happening is that the power is being transferred to larger length scale. And this is sort of a proper inverse cascade. And this, as far as I know, this only happens, I mean, this dramatic inverse cascade happens only when you have a lot of helicity. So it seems to me that helicity is crucial for the survival of these causal fields. And in fact, I can also, so this can be made more quantitative. So here, I don't know if you can see, it's a slight gray, but it's the same plot, and you can see that this peak is moving to the left. And what happens as this peak moves to the left is that the magnetic field becomes maximally helical. And maximally helical is kind of defined over here, where the two power spectra that we talked about are actually related. So the power spectrum is k by 2 times the helical power spectrum. And in this paper by Kaniashvili et al., they find that this power law over here is k to the 4. And yeah, and okay, this is an assumption. So okay, but the important point is that here it's k to the 4, and actually you can track how fast this peak moves to the left.
We have a question here.
Sure.
Go ahead, Masood.
I wanted to ask that if there is magnetic helicity here, can it be transformed into fermion helicity, and we have like produce some kind of chiral imbalance in the universe?
Mm-hmm. Yeah, so I'll discuss that a little bit. Maybe let me just go on because I'm a little short on time, but I will get to chirality in just a little bit. So the first thing is, if you have helical magnetic fields, can you tell that that the field is helical? And remember, I was showing you the morphology of blazar halos. When you have helical magnetic fields, then the shape of the halos, they change, but they also get twisted with respect to each other. So so this yellow curve over here is kind of showing the twisting as you go to lower energy photons. So the highest energy photons come directly, but as you go to lower energies, they kind of twist to the left. And we did a simulation, and you can kind of see the twisting effect happening. And so the question is, if you look at blazars, can you actually detect helicity of the magnetic field? And so with Toshiro and I, we considered the statistics, which is we take photons of 3 different energies related, ordered in a particular way, and we look at photons in a particular disk around the source, and we can form this triple product. The direction from which the lowest energy is coming across the direction from which the middle one is coming, dotted into E3. And the point is that this is a parity odds statistic. So if you have a parity odds statistics, it is sensitive to the parity odd effects that are happening, and in particular to the helical part of the magnetic field. So if the helical part is 0, then you expect Q to be 0. And if the helical part is not 0, then you expect this to be non-zero. We improved the statistic a little bit later, but let me just work with this particular formulation. So we then went to Fermi data, and we said Q is on the y-axis, and this R, the size of the disk over which we're counting photons, is on the x-axis. And then there are different energy combinations, E1, E2, E3. And we were asking whether Q is 0 or non-zero in these plots. And we were getting Q to be non-zero at about 3 sigma. But there is a question that there could be galactic foreground contamination. Even though we tried to mask out the galaxy, there's always some residual contamination. So so this is suggestive, but I wouldn't really take it as it is. And but if you have this, then it gives you about 10 to the minus 14 Gauss on 10 megaparsec scales. So I know that Aspelin et al. Are looking at this in more detail, and maybe others will get interested in this technique, because the technique, I think, is very powerful, because by choosing different energies, you can actually look at the whole spectrum of the magnetic field and not just say whether it is there or not, but you can get to the whole spectrum. So so now what does the spectrum look like? So here's the log EM, here's log K, and you have something like this. And here you're saying it's K to the 4, as we discussed. And I think this gets cut off at about the dissipation scale, which is parsec to kiloparsec by Banerjee and Jadamzik. And then if you believe any of these Blazar results, then at about 10 megaparsec or so, you have some sort of measurement over here. And you also have that the field is maximally helical. So then, given this point, given the spectrum, given the dissipation scale, you can kind of estimate the energy density in a magnetic field, and that is like 10 to the minus 10 Gauss squared if this dissipation scale is a kiloparsec. The magnetic to photon energy density turns out to be about 10 to the minus 8. And the helicity density, you can also work out, because you're saying it's maximally helical. So you get some numbers over here. And so if you believe all these observational things, then these are sort of target parameters that you have to explain if you are going to come up with some mechanism for the origin of the magnetic fields. Now it turns out that the electroweak, the way we discussed it, about 6% energy, can match the energy requirements, but it looks to me that the sufficient helicity will require new physics. And this is just a side note that if you have 3 times 10 to the minus 10 Gauss on kiloparsec scales, then galaxy formation will compress it to 3 times 10 to the minus 5 Gauss on 10 parsec scales, which is kind of comparable to what you see. So that's sort of explaining that golden box that I drew. Okay, so here's that plot once more. If you have baryon clustering that picks out this point, the blazar numbers are sort of giving you a spectrum like this. If you had inflation, then the spectrum would be something like this. And this is quite close to the quasar and other bounds, but I think there's a little wiggle room over there. Okay, so the most interesting thing that for particle physics side is what's the origin of helicity, and here a natural connection exists between magnetogenesis and baryogenesis, because the sphaleron, which is necessary for baryogenesis, you can think of it as a sort of as a twisted monopole antimonopole pair. These are magnetic monopoles. So, so if you have to produce baryons, you go through the sphalerons, and then you have to produce a monopole antimonopole pair, twist the antimonopole by 2 pi, and then have the monopole antimonopole annihilate once more. And so it's not surprising that this process would actually produce twisted magnetic fields. Twisted magnetic fields is just helical magnetic field. So for every baryon number violation, you get a certain amount of helicity, and you can relate the two, and the helicity is about minus, because it turns out that they're left-handed if you want to produce baryons. And it's some number, and then there's the number density of baryons divided by alpha, the fine structure constant. So, so the helicity density to baryon number density ratio in this way, if you do H by NB, is about 100. However, if you look at those numbers that I gave earlier, and you ask what is the helicity to what is the helicity to baryon number density ratio from those numbers, that turns out to be 10 to the 24. So clearly there's a huge discrepancy here. And if any of this is to work, then this large helicity needs an explanation. You probably need more CP violation, and you need some amplification of the helicity. So let me just check the time. Yeah, I have a few minutes. So if you have, so one way to amplify the helicity is to use chiral effects. And if you have a magnetized chiral plasma,
could you try again?
So there's this, in a magnetized chiral plasma, the current, which is the chiral current, is proportional to the magnetic field. And this is like Ohm's law, except there you have J is proportional to E, here you have J is proportional to B. And then several people have discussed chiral-MHD. The evolution of the magnetic field is given an advection term, diffusion term, chiral vorticity, and then a chiral magnetic term. And then there's a chiral anomaly equation. I won't get into this very much, but I want to get to the result, which is that if you decompose B into left and right circular polarization modes, then you can solve the equations, and first done by Joyce and Shaposhnikov. And basically, the spectrum starts looking like this, that you have one of the polarizations has a peak over here, and the other is just decaying like this. So if you work out the helicity, then you find that the helicity grows exponentially. However, it saturates at a level which is given by the chiral asymmetry at the initial time. So unless you have a huge chiral asymmetry, this will not suffice. And so this raises a lot of questions, and I don't have answers to all of them. But one idea would be to start doing serious electroweak simulations and somehow include the effect of fermions. And something that's more a question for you experts, how do we include these fermions in our simulation of the electroweak phase transition? And of course, the question is if the medium can be chiral. And then I've asked this of Igor a few times, but we have to start thinking more seriously. What would be a good description of the chiral-Electroweak plasma? And can there be undiscovered large CP violation? And of course, if you include all the relevant physics, then can you increase the helicity of the magnetic field? Now, maybe you have to go beyond the standard model. Then maybe there are more questions. Can axions play the role of a chiral asymmetry, like the delta mu, the chiral asymmetry could be given by the time derivative of the axion field, or maybe baryogenesis just doesn't work, and you have to go to leptogenesis. Sort of switching things around, some authors have considered the opposite scenario. They recognize that there's two problems. One is magnetic fields, one is baryons. Maybe we can start with magnetic fields and generate baryons. Okay, I would like to conclude. So there are several observations and lines of reasoning that point to maximally helical magnetic fields, maybe 10 to the minus 14 on 10 megaparsec scales. And also sub-nano Gauss fields at kiloparsec scales. So this is the hints, the suggestions, but we still need a sort of a WMAP moment where we can start putting error bars. And remember, in the WMAP, you had the scatter of data points before WMAP came, and then WMAP just put a nice smooth curve. So maybe we still need that WMAP moment. I don't know what that will be, but. And then it looks like the electroweak phase transition can dump quite a significant amount of energy in magnetic fields. But the problem is more with the large helicity that does not seem to fit within the standard model. So then maybe we need some new particle physics, and that new particle physics might serve two purposes. One is to generate the magnetic field helicity, and the other is to generate the cosmic baryon asymmetry. And for that, you would need large CP violation, maybe the chiral magnetic effect, maybe kinetic helicity, which might be useful. I didn't get a chance to discuss. Or maybe there's something else which we just don't know. All right, that's the end. Thank you.
Well, thank you. Thank you very much for a very interesting presentation. Now it's time for questions. And I see already people starting to raise their hands. So Masood, you may start.
Sorry. I was thinking that if the universe is magnetized and it has a chiral imbalance and something things like that, is there, I mean, can the universe be isotropic and at any scale with all of these things happening?
So you're thinking of that the magnetic field breaks the isotropy of the universe?
Yes, the magnetic field plus, if the magnetic field is present, and there's also chiral imbalance, so you will have a chiral current from somewhere to somewhere else. So there is a direction. I mean, maybe I'm not understanding the picture, but
yeah. That's hard for me to imagine. The breaking of rotational symmetry would be hard to imagine unless you had something like inflation or something which sort of created a super horizon field. So yeah, so yeah, I don't. Yeah, I don't see how one would break the isotropy.
Thank
Okay.
you.
Can I continue here?
Go ahead.
Okay, conclusion here, the last point, CP violation, we know that for a long time before, a huge CP violation. Second one here comes on a standard model here. Can you, next slide here, slide before. At least, conclusions before.
Sorry, the audio wasn't completely clear. Can you repeat?
Oh, well, we know that the standard model, we have a huge CP violation in subtle ways here. Matter versus antimatter here, right? We know it for a long time ago here. And do something new here. Can you slide before?
Can I?
The example here. For example, here, number one, I'm fan of this one here. Second one, then here. The second one, I'm not sure. My statements here.
I see.
I mean, 4 questions here. Can I ask a question here? Talks about baryons here, protons and neutrons, right? Not beyond. Protons, neutrons, we're not beyond.
Sorry, I'm not understanding the question. Igor, can you clarify?
Baryons. You talked about, it seems to me, protons and neutrons, not strange baryons, right?
Well, at the time, it can be any type of variance. It could be also in the form of quarks. I don't think it has to do any specific variance. Baryon number and then whatever it happens to be.
Yeah, but
it's more subtle here.
But today it's, protons and neutrons,
So, did you get the answer to the question, or you want to sort of rephrase it? I am not.
No, I mean, we know that here, axions, I'm a fan of them. You should find it. Leptons, actually, I'm a fan of this. They understand that matter versus antimatter comes from quarks, but leptons here, and tested a neutrino CP violation. That's my statements here.
Well, but I suppose the idea is that in some grand unification theories, actually in many of them, it's actually B plus L that can be violated, and B minus L is conserved. And essentially, playing off this idea, there are some models of baryogenesis which are basically considering this possibility, and that's how you could actually go from one sector, for example, leptons, to baryons. And in fact, maybe next colloquium next week will be sort of partially related to this.
Yeah.
So there are many, many different models for baryogenesis. And I assume here there was no specific statement which one of them is sort of at play.
Yeah, as long as the baryogenesis was going through sphalerons or some kind of sphalerons, then the connection between magnetic fields is there. Yeah.
Edward, you're trying to ask something?
Yeah, I just want to say that the paper which was already mentioned here, we kind of recalculated CP violation in the sphaleron explosion, and we get numbers which are in the ballpark of 10 minus 10. So there is a scenario which get from sphalerons baryon asymmetry directly in a standard model. Even if this calculation is not completely correct, the question, what exactly standard model KLM matrix does and what kind of asymmetry it produces is still the old unanswered question.
Yeah,
but what about magnetic field? Of course, each sphaleron create polarized leptons, most specifically electrons, and electron give the chirality to magnetic field very actively by this chiral hydrodynamics. But what happened next, I don't know. So all these arguments, how that relates to observation, that is not something I know.
But if there's a way to get more helicity, then I think it would be very valuable. Yeah.
Well, we get, it's electroweak spheron, so it get left-handed electrons, yes, as a result. And then they give all their chirality to photons. But the question is what happened, then there is long time of this magnetohydrodynamics and whether, yeah, as you said, chirality cannot die, but it can move in spectrum. And that is subject outside of what I know.
Okay.
Okay, other questions?
In fact, I mean, who talks about next week here, but after connection is dark matter, didn't mention dark matter.
Right. Well, actually, you do want to come to the next colloquium next week.
Okay.
There will be something connected to that, I believe.
Yeah.
So anyway, any questions to Tanmay, though? Go ahead. Arvind, I'm not sure if I pronounced it correctly.
Hello?
Yeah.
Is it clear? Voice is clear. Okay. So in one of the slides that I talked about the magnetic field from the electroweak field transition. So my question is, in the late time, like when the Higgs field take wave, and after that when it comes on minima, so it produces the magnetic field on all scale, right? So okay.
Sorry, it produces a spectrum.
Yeah, it's spectrum magnetic field as he talked about. So
yes, it would produce us. So you know the total energy density, you know the spectrum, and then the MHD. Then you would have to evolve it using the MHD equations, and then get the magnetic field today. But the evolution depends on how much helicity is in that field. And if the helicity is small, then you would expect the field to be dissipated.
So my question is, what happens, like as you pointing out, like so the evolution depends on the how the MHD equation, when you put all the terms, how it evolves with the time. So but we see for present time that at the galactic kind of scale, the magnetic field is very high, but on the large scale, like megaparsec or something like that, or supercluster scale, magnetic field is very small. So how the evolution?
So that's the K to the 4 spectrum. So it goes as one over the length scale to the 4.
Okay.
So that's why you can have small, weak magnetic fields on blazar scales, but stronger on say galactic scales, on kiloparsec scale. Yeah.
So isn't it like the dynamo kind of the mechanism that increases the strength of the seed magnetic field, that it's on the smaller scale or in compare with the large scale or something like that?
Well, so in this case, if this picture is true, then this field could be compressed into the galactic field, and you might need a little bit of dynamo amplification. This is not to say that the dynamo, nothing is wrong with the dynamo. In fact, I've been told by my MHD friends that you need the dynamo just to keep the galactic field alive. So it's so there's always a dynamo. But if you're in this region, in this golden box region, then you're pretty much there, and you don't have to assume any maximally efficient dynamo and things like that.
Okay, I don't see any other questions. So I think it's about time to wrap it up. I would like to thank again Tanmay for a good presentation. Thank you everybody for joining us. I think it was very interesting for thinking about these ideas, and
thank you all. Yeah, thank you all.
Have a good day, everybody.